Welcome to this video on elements and the periodic table. I'm Arnold Villaro, and you can reach me at the email shown on the screen. The periodic table is a chart where elements are arranged according to their atomic numbers. It also organizes them based on their chemical and physical properties. The periodic table is fundamentally divided into two main components, A groups and B periods. Groups are the vertical columns in the periodic table. The group number indicates the number of electrons in the outermost shell of the elements within that group. Periods are the horizontal rows in the periodic table. The period number indicates the total number of electron shells an atom has. This slide is a title slide for the periodic table. Electron configuration is the distribution of electrons of an atom in the electron shells. This distribution indicates the specific electrons in each energy level of the atom. The rules for electron configuration state that the first shell holds a maximum of 2 electrons. The second and third shells can hold a maximum of 8 electrons each. Any remaining electrons after filling the first 3 shells are placed in the fourth shell. Here are examples of electron configuration. Sodium Na is 2, 8, 1. Fluorine F is 2, 7, and argon Ar is 2, 8, 8. We now have some problems for you to consider, determining the electron configuration for potassium K, chlorine Cl, and neon Ne, given their electron numbers. The trends in the periodic table are discussed in terms of atomic radius, electronegativity, electron affinity, and ionization energy. Atomic radius is the distance from the center of the nucleus to the outermost shell. It decreases across a period and increases down a group. This image illustrates the concept of atomic radius, showing both a single atom and a diatomic molecule of hydrogen. Electronegativity is the ability of an atom to attract an electron in a chemical reaction. It decreases down a group and increases across a period. This graphic provides a simple illustration of electronegativity, showing an atom's tendency to attract a bonding pair of electrons. Electron affinity is the amount of energy released by an atom after gaining an electron while in a gaseous state. Electron affinity increases across the period, and it decreases down the group of the periodic table. This diagram visually represents electron affinity, showing an atom in a gaseous state gaining an electron to form an ion. Ionization energy, or IE, is the minimum energy needed to remove one electron from an atom in a gaseous state. IE increases across a period and decreases down a group. Effective nuclear charge is the net positive charge experienced by an electron in a multi-electron atom. It increases across a period and also increases down the group. This slide is the title slide for the summary of trends in the periodic table. We will now explain the general trends for alkali metals, halogens, and noble gases. For alkali metals, melting and boiling points decrease down the group. Reactivity increases down group 1 elements, and density generally increases, except for potassium. Alkali metals have several uses, including sodium for extracting silver and gold, and lithium for hardening aluminum and lead. Potassium is used in manufacturing fertilizers. A mixture of potassium and sodium is also used as a liquid coolant in nuclear plants. For halogens, the melting and boiling points increase as you move down the group. Conversely, the reactivity of group 7 elements increases as you move up the group. The density of halogens is another trend to note. It decreases as you move down the group. Halogens have practical uses. Iodine prevents goitre, chlorine kills germs in water, and bromine is used as a photographic chemical. Furthermore, fluorine is used in the production of toothpaste. Regarding noble gases, their density increases down the group. Melting and boiling points decrease from helium to argon. Noble gases are known to be inert, meaning they are very unreactive. Inert or noble gases are used to fill electric light bulbs and as insulators in arc welding, like argon. Neon is used in advertising signs, flashlights, and disco lights. The physical properties of alkali metals include their high reactivity and having the largest atomic radius within their respective periods. Alkali metals are soft and easily cut with a knife. They have relatively low density and float in water, and they possess low melting and boiling points. Chemically, alkali metals burn in air to form white solid oxides and react with water to form an alkaline solution and hydrogen gas. Examples of these reactions are shown. Alkali earth metals are all metals with a shiny silvery white color. They are generally harder and denser compared to group 1 elements. These metals give characteristic colors when heated in a flame. Their atomic and ionic radii increase smoothly down the group. The chemical properties of alkali earth metals involve reacting with oxygen to form metal oxides and reacting with water to form an alkaline solution and hydrogen gas. A specific example of this reaction is calcium reacting with water to form calcium hydroxide and hydrogen gas. Finally, for the physical properties of halogens, their atomic radius increases as you go down the group. Their boiling and melting points also increase down the group. The reactivity of halogens increases as you move up the group, with fluorine being the most reactive and iodine the least. Their physical states vary, such as fluorine being a pale yellow gas and iodine being a dark gray solid. Chemically, halogens react with group 1 elements, such as sodium, to form salts like sodium chloride. This is a defining characteristic of halogens. Halogens also react with water to produce acids. For example, chlorine reacts with water to form hydrochloric acid and hydrochlorous acid, as shown in the equation.